Hello, and welcome to the session on Earth Engine and Deep Learning Part 1. In this session, we'd like to highlight the capacity building potential, technical prowess, and the regional, national, and local impacts that are generated through the SERVIR and Google collaboration. In this session, we're going to describe use cases to illustrate how SERVIR uses the deep learning capabilities of Earth Engine and the Google Cloud Platform to power environmental monitoring applications at scale around the world. In the first part, I'd like to introduce Tim Mayer, who is the science coordinator for the SERVIR Kush and Himalaya hub of the SERVIR network. Tim is a researcher who is doing fabulous work on the integration of Earth Engine and TensorFlow and has been a real force behind the SERVIR TensorFlow working group, who are producing all kinds of interesting outputs and regional monitoring tools in the various SERVIR hubs. So Tim and his collaborators are going to talk about that work right now.
Hello, I'm Timothy Mayer, NASA SERVIR Regional Science and Coordination Lead for the Hindu Kush Himalaya Hub. Also joining us through video and in the Q&A session is Nyein Thwal, who's a geospatial data scientist for SERVIR Mekong. I'm excited today to talk about the SERVIR program and how SERVIR, with great collaboration from Google, continues to build geospatial capacity for leveraging Earth observations around the world. Overall, this main session is focused on Earth Engine and deep learning and capacity building. And firstly, I wanted to start off quite broad with a global perspective, laying out the SERVIR program's approach. And next, I wanted to take a step forward and talk about how the SERVIR program has made strides to leverage Earth Engine and grow capacity of the implementers around the world to utilize deep learning and via TensorFlow for addressing environmental challenges. Moving even closer, I wanted then to dive into a few co-development examples that have been generated from the TensorFlow working group for folks to get more insight into the collaborative environment that is crucial for exploring new methodologies. And finally, we wanted to get down to the ground level and talk about a real-world example of how SERVIR is using Google technology to work with communities to address environmental issues. Once I move through this broad overview, you will then be hearing from representatives from the Greening Prey Long USAID Cambodia mission, who are project partners. And lastly, Nyein will then pop the hood on the forest alert system to talk about the new methodologies of how SERVIR Mekong is using TensorFlow and is exploring these new workflows. I hope you're as excited as I am. As all of you are well aware, the communities around the world face unique and complex issues. And oftentimes, the data that is absolutely necessary for addressing these issues is limited, difficult to use, or it requires extensive training, knowledge, and resources. This need to connect regions, countries, and communities to data is the reason the SERVIR program came into existence over 16 years ago. The motto of SERVIR is to connect space to village, and through this unique joint initiative between NASA and USAID, as well as leading geospatial organizations in Asia, Africa, and Latin America, SERVIR partners with these regions to address critical challenges in climate change, food security, water and water-related disasters, land use, and air quality. And SERVIR co-develops innovative solutions through a network of regional hubs to improve resiliency and promote sustainable resource management at local, national, and regional scales. This session will primarily focus on an example from the land cover and land use and ecosystem theme. However, SERVIR is quite broad and collaborates across 4 thematic areas I had mentioned before. And for folks who are interested in more detail on those thematic areas, feel free to check out the SERVIR service catalog, which provides far greater detail. As mentioned also, SERVIR works around the globe with 5 dedicated hubs, one in West Africa, Eastern Southern Africa, Amazonia, the Hindu Kush Himalaya Hub, or HKH, and SERVIR Mekong, which you'll be hearing more from shortly. And briefly, you can see the breadth at which we operate with many different focus countries that we collaborate with. So as I mentioned a few slides back, SERVIR is a unique program due to the level of partnership and collaboration. And this is an extremely small snapshot of the organizations that comprise the SERVIR network. As mentioned, NASA and USAID, along with the 5 regional hubs, and also the accompanying hub consortium members make up a lion's share of the SERVIR network. But I'd be remiss if I did not mention the private sector collaborators such as Google, and of course, the broader US government collaboration, international and NGOs who contribute. And finally, SERVIR works with 20 plus universities and research centers. In short, the SERVIR network is vast, and by far that's the greatest strength to the program. I wanted to then briefly highlight why SERVIR is unique. SERVIR relies on a demand-driven model and co-develops services with local and country level and regional partners. And critical to the success of SERVIR is the process of co-development, and the process of co-development of services that are inclusive and representative of women and indigenous communities into the needs process and the needs assessment process to ensure that the services that are developed are effectively contributing to the communities. And SERVIR is unique in that because the activities and the services that are co-developed are produced to be lasting and useful tools. Specifically, SERVIR prioritizes trainings and resources for capacity building as part of the service delivery so that the geospatial services that are developed can be sustained by the communities and the regional implementers. So as I mentioned throughout, training and dedicated capacity building is a key aspect to the success of services. And specifically, SERVIR hubs are developing training series focused on empowering women and girls in the STEM field. And also, in addition to these in-person trainings and subject matter expert trainings, SERVIR also continues to produce practitioner-oriented training content, such as the SAR Handbook, which is designed for forest managers and individuals conducting MRV efforts to have a comprehensive set of methodologies at their disposal. So on the vein of capacity building, SERVIR has had a long collaboration with Google and the Earth Engine team. Back in 2019, the SERVIR Science Coordination Office at the Marshall Space Flight Center hosted the 2019 state-of-the-art land cover methods meeting with Silvacarbon. Following that, folks from across the SERVIR network attended the Geo for Good 2019 summit and participated in a build-a-thon event that directly focused on and leveraged TensorFlow. Following that week, SERVIR then hosted a technical exchange and had great support from Nick and the rest of the Earth Engine team. And through the course of that technical exchange, the need for a TensorFlow working group was established. We then formalized a network-wide group that would explore novel methodologies and deep learning applications to grow our collective capacity. And specifically, we oriented each of the teams participating to focus on a service and an environmental challenge in the region. And we then proceeded to have bi-weekly meetings since 2019. We also then held a 2020 technical exchange virtually, and of course participated in the Geo for Good 2020 summit with regionally dedicated SERVIR sessions highlighting the efforts from this working group. So it's really exciting now that we've had 2 years of the TensorFlow working group to see the array of milestones that have been generated. And in the past few months alone, folks who participated as part of the TensorFlow working group have published 3 papers focusing on agricultural mapping, flood inundation and surface water mapping for flood response, and impervious surface mapping, all of which were born from the collaboration of the TensorFlow working group. So as you can imagine, the TensorFlow working group mirrors the broader diversity of the SERVIR network and has a wide level of participation from a huge number of organizations. And specifically, as a portion of our dedicated meetings, we also invite subject matter experts, leaders in the field of deep learning, and practitioners and even novices to come and present their research to help facilitate that collective capacity building. And this is in the portion in the talk where I would put the plug. If you're interested in knowing more and participating in the TensorFlow working group, feel free to talk to us at the Q&A session because we welcome all interested folks into the working group. Now I want to drill down for 4 quick examples of some of the research that's being conducted by the group. First, here on the left, we see work from Abina, who's contributing from the West Africa Hub, who developed a CNN model for effectively predicting illegal gold mining efforts in Ghana, and with an end-to-end workflow in Google Earth Engine and TensorFlow. And on the right, we see work here from Katie Stratman, who developed a DNN and compared that to classical machine learning methods for detecting and mapping mangroves in Africa. Here on the left, we see a snapshot from Lucio Villa's work from SERVIR Amazonia's hub, and he and the team have developed a UNet approach for detecting illegal logging efforts using Planet NICV data. And on the right, we see efforts from Tunisia from the SERVIR HKH hub, who's been leveraging a UNet as well for detecting impervious surfaces. This is just 4 really fast examples of some of the ongoing work and content that's being presented, discussed, and is a source of collaboration and a way for us to leverage the Google Cloud, TensorFlow, and Google Earth Engine platforms to address environmental challenges. Now, with the time remaining, I wanted to go down to the ground level, as I mentioned at the onset, and hear from some of the end users and how these approaches can be impactful.
Working with SERVIR Mekong to get the 3 loss alert from the radar-based imagery during the rainy season. We got the 3 loss alert from radar imagery called synthetic aperture radar alert, and with this alert, community team to investigate the area of 3 loss and then take action.
With the collectors online from the alert system that SERVIR Mekong helping us in Cambodia to alert the patrol ranger, to alert the community patrol is very important.
Hello everyone, my name is Nyein and I work as a geospatial data scientist in SERVIR Mekong program. And today I would like to present mapping forest disturbance using TensorFlow and Google Earth Engine. As all of you know, forest is a very important natural resource for human beings. So maintaining those forests is also vital task. So forest disturbance alert is a very important information to maintain those forests. So these alerts can be created by using machine learning algorithm with training data and many satellite imagery. So today I want to present how we will be creating this disturbance alert using radars, Sentinel-1 imagery. So why we are using radar forest disturbance? So currently for the forest alert data, we have data from University of Maryland GLAD program. However, they use Landsat 8 optical imagery, and these data are not inconsistent during the rainy season in Cambodia. So that is why SERVIR Mekong plan to develop radar-based alert to allow better monitoring during the monsoon rainy season in Cambodia. So here is our study area, Preland Wildlife Sanctuary, and it was designated in 2016, and it has total of 431,000 hectares. And we also include another surrounding 2 sanctuaries near GPL the expanded study domain allowed for a large number of training data, and that will have that final model to generalize for regional monitoring. And this GPL and its surrounding area have experienced very high rate of deforestation every year. So we are planning to focus this area as our study. So here is our system overview. So first, we created our training dataset in Google Ad Engine. And after that, we create TF record and export in Google Cloud. And after we export in Google Cloud, we use those TF records in our virtual machine to train our deep learning model. And after we got our trained model, we launched those models in Google AI platform in Google Cloud again. And after that, we create inference in Google Ad Engine to get our output results. And for the validation, we use Collect at Online CEO to validate with NIFI planet imagery for our SAR alert. And next, before moving to model architecture, I want to introduce a little bit about TensorFlow and Keras. So TensorFlow is an end-to-end open source platform for machine learning, and it has a comprehensive, flexible ecosystem of tool library and community resources, and developer can easily build and deploy machine learning power application using TensorFlow and Keras. And Keras is a Python interface for artificial neural network, and it acts as an interface for TensorFlow library. And in Keras, there are many available pre-trained models that we can use as a transparently in our network. And here are the example model like Exception, VGG60, VGG19, ResNet, and MobileNet, etc. And later in our architecture, we will be using MobileNet as an encoder in our architecture. So here, as all of you see, MobileNet, the size of MobileNet is very small compared to other models. It only have around 40 to 60 megabytes, and its accuracy is quite comparable to other models. So that is the reason we are using MobileNet in our architecture. And here is our model architecture. So our main model architecture is UNet. So the architecture shape is like U shape, and there are 2 paths in UNet, an encoder and decoder path. So here, this left side is encoder path, and for the encoder path, we use MobileNet v3 as some block from MobileNet v3 as an encoder. And MobileNet v3 is the advanced version of MobileNet v2, and it includes Squid and ASICs as the output after the bottleneck residual block of v2. And the accuracy of v3 is better than the MobileNet v2, and we are using those as an encoder in our architecture. So here we have 128 into 128 size image, and we encode it to 6432 NT8. And after that, we decode these image patches, and at the end we got our original image size 128 into 128 size image. And at the end, we feed through with sigma activation function to convert output value into probability distribution or two classes, disturbance and no disturbance, as the output. So for the detailed methodology, first, we perform random data augmentation to generalize our data sets, and we just did augmentation using 0, 90 degree, 80 degree rotation. And we optimize our model with Abdan Optimizer, and we train using patch size of 60 and approach, total approach of 14 for our model. And for the loss function, we use dice lot as a loss function. And for the performance evaluation, for the training and testing, we calculate categorical accuracy and advanced call, recall, and precision. And these are the figure in the left show the accuracy of training and testing data sets for both of ascending and descending orbit. And the table here show the model validation result for the ascending and descending model. And for the ascending orbit, the accuracy is 0.92%, and descending orbit, the accuracy of 0.90%. So ascending orbit has a little bit higher accuracy than descending in our model. And for the validation, we perform independence validation. And for this independent validation, we collaborate with US 8 Granny Preland team and other NGO and university team for this validation. And here we use Collect at Online for the past year from 2018 to 2020 with planet imagery. And we create some example or strategy for the validation. And in the right figure, you can see how we can use CEO to validate our imagery. So we use 3 categories and we validate. And this is the result of the validation. So this is independent validation result for 2020. And here what season consider June to August in the table. So in here we create stratum as you see in the figure. So glad dry, sad dry, and dry, glad dry, wet, and sad dry, wet, September, October, November, and no disturbance with the total of many points. And here we can see we got highest accuracy for both of glad and sad dry season. And for the wet season, we don't have, the accuracy is not good. And this is the system output. So for the output, we will be creating Google Ad Engine app for the user to support for the user. And the alert will be created every 6 days when Sentinel, when overpass and update inside alert system. And this app engine tool can support user to identify default interest, and they can view SAR alert along with GLAD alert and Sentinel to image. And they can export alert by predefined protected area and its date. And after that, they can process further analysis in their designated tool. Thank you everyone for your interest.
A huge thanks to the entire SERVIR network who enabled this capacity building work. And please reach out to both Nyein and I with any questions that you might want to get addressed at the Q&A section. And also, if you're interested in participating in the TensorFlow working group, please reach out to both of us. Thank you.
Okay, thank you very much, Tim and Nyein. It was really fantastic to see all the great work that the SERVIR TensorFlow working group is doing and that the SERVIR hubs around the world are doing, and leveraging Earth Engine and TensorFlow to have some really great impact. So thank you very much and happy coding.